Here we are on a nice 3 a.m. 2:56 actually. I feel like that time really sets the vibe. We have here a chemistry problem that I will now do in this atmosphere right now. Just whatever. Yeah, atmosphere is what you make it to be. But yes. So let's see. This stuff's not really important. It just says one resonance contributor, minor, is given. Why would they give me the minor one? I don't really understand why. But there's nothing that... Ugh, that's so horrible. So, in a molecule, you can assume... I mean, it says, I think, that this is all closed shell. Yeah. Sorry. So, yeah. Excuse me. So this is closed shell, which means every atom here has 8 electrons except this one. Okay? Now, that's a little weird. This should have 8 electrons. Because this is boron. Boron only has 3. So, if it shares all 3, and every time you share an electron with another atom, you share one, the other atom shares one, apparently. So, you have 3 electrons, you only be able to get 6 in all, because, share 3, you only get 3 back. So, it has 3. Can't do another bond, because it doesn't have another electron. Now, it can... If you were to draw another bond, well, now some people would just be like, okay, so the oxygen has a plus formal charge, and this has a negative formal charge, because the lone pair would have counted as 2 electrons, now it just counts as 1, but I don't care how other people explain it. This is the way to explain it. In a bond, it's presumed that oxygen has one of these electrons, and boron has one of these electrons, and they're sharing with each other. So according to this, then, instead of having 6 electrons as it did, this was 1, 2, 3, 4, 5, because one of these was oxygens, and 6, one of these was oxygens. Now, it has 1, 2, 3, 4, 5. Now both these electrons aren't oxygens anymore. Now technically one of them belongs to bromine, and the boron decided to share with oxygen. Oxygen decided to share with boron. So it's like presumed that one of these electrons was actually borons. So if it's saying, okay, one of these electrons is actually borons, so in boron's perspective, it has 1, 2, 3, 4 now, instead of just 1, 2, 3. So you give it a negative charge because you're saying, okay, it has 1 more electron than it normally would have. You give this a positive charge because it's 1 less electron than it normally would have had. Because apparently oxygen is supposed to have 6 electrons because it has 6 protons. If this makes sense. You have as many the idea is that you have as many electrons as you do protons. So oxygen normally has 6 valence electrons. Valence, so to explain what valence electrons are, they're just outer electrons. There's a really easy way to see it to understand this. So like essentially, we're able to tell when an atom has, instead of just going around, so This is the nucleus. So instead of just placing electrons here, we're able to tell, okay, now we're placing electrons like here. And okay, now we're placing electrons here. And so, and one way we're able to tell that is because this, presumably, like, it's full. You know, once you go here, you add another electron, you add it to the second energy level, which means that, okay, the first energy level must have been full. Thus, we're here, okay, the energy, this is when the energy level became full. Thus, it's stable. This one's stable too. This one's also stable, because these are all when the energy level becomes full. Over here is when you start adding to the newest one. Now, that electron is very much an open space. So these elements are very, I guess, reactive. It's very easy to take the electron of these elements because it's just out in the open. These elements really want an electron because they want to be full, is the assumption. And this assumption's made because these elements are highly reactive. It's presumed that they are taking the electron from here. And there's more additional explanation on why it's thought that the reason this is reactive is because it's taking the electron. That's all we're going to for now. So, you're probably wondering why I said, oh, this sucks. And I will tell you. So let's see. It absolutely is bad because oxygen, according to the table I showed you, it'll be closer to filling its shell, and as it gets closer, it wants to more and more wants to fill its shell. Part of the reason is because as you get closer to filling your shell, you have more protons. Like as you go from here to there, you have more protons here. So it's like the electrons are like the same energy level, but now there's more protons, so it's pulling more of them. So yeah. So going back to here. This sucks because oxygen, according to here, has one less electron than it normally would. That's weird, because oxygen has one of the strongest pulls on electrons. So why out of all the atoms here, nitrogen and carbon, why is it that this oxygen is the one with a plus charge? I would say that, I'd say that's it'd be more likely to be nitrogen. Nitrogen shouldn't have this negative charge. If anything, oxygen would have a negative charge. Because, again, it wants an extra electron. It wants that electron. It's more likely to have an extra electron. But you might be wondering, okay, but carbon, if you look at carbon, it's like this is carbon, nitrogen, oxygen, fluorine, and then full shell. Okay. Yeah, so you're like, okay, but carbon's even further. It has, one less proton, and it's less protons pulling on them, same energy level, so why is carbon not going to have the plus charge? Well, this is because we already know that this is the structure of the molecule. And this carbon, actually, yeah, it could actually be, yeah, technically it could also be, it's weird because carbon would have to be connected, So, thing is, carbon has 4 electrons. Now, if it shares all of 4 of its electrons, then it'll have an open shell. So, if it has 1 less electron, you're not, no matter what you do, you can't get it to filled shell. Nitrogen, however, it'll make more sense with nitrogen in explaining this. Nitrogen, how you say, nitrogen has 5 electrons. So, even with 1 less electron, if all of those electrons are shared with another atom, it'll still have 8. Normally what happens is that it's at 5. It only needs 3 more electrons. So it'll share 3 of the 5 electrons. Yeah, so 3 of this 5. Yeah, so it'll share 3 of the 5 electrons, which would, add 3 to the total, so you'd get 8. Or another way to explain it is, you're saying, okay, you have 2 electrons you're not sharing, plus 3 that you are sharing. You just get 8. It gets very intuitive, though. Like, when I think about it, I just think it needs 3 more electrons. It's going to form 3 bonds to get those 3 electrons, because it gains kind of an electron with each bond. Oh, yeah. So, but carbon, yeah. So it'll be at 3, which means there's no way it can get to 6, even if it has a bond. Even if all those are involved in a bond, it's not going to be able to get to 8. 8 is what needs to be, is what you need to have to be a closed shell at this level. So, yeah. So now we're at nitrogen. So I can't really do carbon, because if it doesn't have a closed shell, it's very unstable. As I showed earlier, those elements that are not reactive, not reactive, are the ones that have naturally closed shells. Every atom here actually has a closed shell. But this one has a closed shell while having had an electron taken from it. This one has 1 less electron than it started out with naturally, I guess you could say. This one has 1 more electron than it would have naturally had 5 electrons. In this configuration, it's shown that it actually has 6 electrons. So you're like, okay, oxygen's more likely to have had 6 electrons. 1 extra electron, which means it would have 7 electrons. So it'd only form 1 bond. Yeah, it'd only form 1 bond. Because, it goes from 6 to 7. So at least it won't form 1 bond to get to 8. So nitrogen right now, you normally need to have 3 bonds, because it has 5, you need 3 bonds to get to 8, but that's not the case. It has, it's only sharing 2 of its electrons, because it has 6. You can see. So yeah. Now, even though I said oxygen's more likely to have a negative charge, let's draw one of these resonance structures actually. So it's going to have the same resonance structure. By definition, has the same connectivity. I am super sorry about how horrible that was drawn. I'm drawing it through my camera. It makes it difficult. I'm changing now. Let's see. It's weird. Not really had an error in drawing that. I usually just, it's been a while. So yeah, the same connectivity. Now, if this has one more electron than it normally has, this one has one less electron than it normally has, then technically, I mean, you could, so this has one more than it normally has. This one has one less than it normally has. Theoretically, there is a configuration where this one electron here is actually here, because then this one has just as many as it normally has. This one has just as many as it normally has. But you might be wondering, okay, but if you give this one an electron, won't it overfill its shell? No, actually, because let's say, okay, so let's say this one has the extra electron, okay? So with the extra electron, it doesn't need to form another bond. So there's not going to be another bond formed. So it's going to have an extra electron, and thus it's going to have one less bond. Now, if this oxygen was already attached to like 3 different things, okay? Osmium, osmium, and osmium, okay? So attached to 3 different things, then you couldn't say that. If it has, like if this was it, then if we got an extra electron, it wouldn't, there's nothing less it can do. It has these single bonds. That's the littlest amount of bond you can have. And resonance structure by definition says you have the same connectivity. So here, okay, attach to this. What if there's a bond, then you know that there's like a double bond, so like the second bond, you have these sort of options. So let's say this one had the extra electron, but it doesn't form the bond. Okay. Now, if it doesn't form the bond, like imagine a bond like if you form a bond, if you took this and form the bond, think of this having 2 electrons now and this having 2 electrons now. But you're saying, okay, this bond, not only this has 2 electrons. So if every single atom here is going to have 8 electrons, then if you break a bond, you should form it somewhere else. You should form another one somewhere else. Because if you break a bond and just give it to one atom, okay, now it's like there's 2 less. Now those 2 electrons aren't shared by 2 atoms. Now it's only shared by 1 atom. So now there's 1 atom that's at a loss of 2. So one way to keep track of this is just by using curved arrows, as they call them. So now this only has 1 electron or so. I mean, yeah, it has 2 less electrons. But this is a different situation, though, by the way, because this technically doesn't have an open. This doesn't have a closed shell, and it says draw all closed shell systems. So even though I said, okay, if you break a bond, now that those 2 electrons aren't shared by 2 elements, now it's only shared by 1 atom. You have to form somewhere else. This is actually saying, okay, there needs to be another bond formed here, because every atom in here has 8 electrons. This has 6 electrons. So thus, if you take this away and bond it, now you technically, now you have 8 electrons here and 8 electrons here. So it's like you gave this one 2 electrons, which is what happened. Like this one literally like gained 2 electrons because both of these are now being shared instead of none of them being shared. So yeah, so now you actually by definition have to have one additional bond than you started with. But yeah, but I'm going a step further. Oh yeah, so that, or maybe instead of that one, you use this one. Okay, so yes. Oh no, this is so, I wonder if you can see. Okay, so yes, so that went there, so this one technically, like one electron here, one electron to that, instead of both electrons to that, so this one's kind of lost an electron, so its formal charge is one positive number larger than what, because electrons are negative, so technically it's like lost negative, so plus one. This one still has both its electrons, so I'll just put them. Okay. So if this is, so I'll start with the nitrogen actually, because the nitrogen lost electrons somehow. Yeah, so it lost electrons. So we can say it lost electrons by saying, okay, one of the lone pairs on the nitrogen is going to go into the bond instead. So now technically one of the electrons don't belong to it anymore. But it's still in its vicinity, so it's still part of its 8. So they're like, okay, donate to this, but now this one has too many, so this one can now yeah, so this one has too many, so now we can say, okay, this double bond is no more, because now it like gained 2 electrons, so it can just give it to this, it can give it to this atom, because remember, the nitrogen just now is bonding 2 additional electrons to this. So I'm just saying that we can move these electrons then, because now it has 10, 2 additional electrons, so now it has 10. So we can distribute, because the goal is to give an electron to the oxygen, essentially. So this bond gave the electrons here, so now this is in a loss, so it needs electrons. This one, now this one needs electrons, that one needs electrons, this can just stay the same. So it gets very intuitive and you get more logic as you keep doing it. That's how you do one of those problems.